Hello, welcome to Progressive Education Society's Modern College of Pharmacy, Nigadi, Pune, in the e-lecture series of in the subject Natural Drug Technology.
In this video, we will discuss about herbal novel drug delivery systems or the novel drug delivery systems that can be applied to herbal drugs. Transferosomes. These are under the category of novel vesicular drug delivery systems. They are vesicles or very small bags or sacs. The sac or the outer membrane is made up of phospholipids. The vesicle is made up of phospholipids, and these formulations are specially designed for targeted drug delivery systems. They have enhanced skin penetration property. That means generally these are used for external application. Because of this, their increased hydration and osmotic pressure, they are able to penetrate properly into the skin, and they are also able to pull the drug inside the skin or through the skin. Now, this is the way how transferosomes act. Suppose these are the transferosomes and these are our various stratum corneum cells with the staggered configuration. The transferosome are able to pass through the intercellular gap, or they are able to dissolve the phospholipids present here, and they are able to migrate through this gap and are able to deliver the drug at the site of the action. We have seen liposomes, and in liposomes we have seen the outer core was made up of lipids or the lipid bilayer, wherein these are the hydrophilic heads and lipophilic tails. The lipophilic tails, they align themselves towards each other to entrap the drug, lipophilic drug, whereas the hydrophilics, that is water-loving core, aqueous core is formed wherein we can load the hydrophilic drug. So this is the TS of a liposome. Now, if you compare this with a transferosome, it is altogether different. The components of transferosomes are in this way. Like that means they have phospholipids. The phospholipids, these blue-colored heads, they are able to form a bilayer, very similar to that in the liposomes. Besides, they also have a surfactant. Now, this is a surfactant. The surfactant is positioned intermittently between the lipophilic core, lipophilic or phospholipid bilayer, and these red colored globules, which are forming uh, the surfactant, they are edge activator. They are also known as edge activator. That means they are able to pull the drug through the skin membrane, because of our skin is also made up of this phospholipid bilayer as well as lipid nature. The surfactant helps penetration of the skin. These red dots are in addition to that of the liposome particles. Alcohol is a solvent that dissolves the drug here as well as here. It is an ampipolar solvent. Besides, they also have a buffering agent so as to maintain the hydrated medium around the transferosome so that they are able to dissolve the lipophilic stratum corneum layers. As we have discussed, these are sac-like vesicles made up of phospholipids for, for drug delivery through skin. They are able to overcome the penetration difficulty faced by normal drugs. Most of our drugs or APIs are unable to pass through the skin, but transferosomes can easily make an access to these drugs. Additionally, these transferosomes, they are very similar to octopus. They can mold their body they are so flexible so as to fit into a smaller cap, so they can change their shape and enter through the smallest pore of our skin, and then they can regain their original structure. This is how they help in penetration. Generally, in the case of herbal, colchicine is used for drug delivery through this mode of uh, drug system. Um, because colchicine itself, it faces the problem very similar to that of an aspirin. It acts as a GI, it has gastrointestinal side effect. It erodes the gastric mucosa when given orally. So this is the better way of allowing the or administrating the colchicine. Advantages of transferosomes: they can deform and pass through narrow constrictions without a measurable loss. There is a very rare law, very less loss of the drug through this mode of entry. They have high entrapment efficiency. That means more and more amount of drug can be loaded into a single transferosome, especially the lipophilic drug is loaded around 90% of the entire structure. It is easy to scale up. Scale up means when you are preparing these transferosomes at lab level, the success rate is good. But generally, for novel drug delivery systems, when you are going on a large scale, you have to modify a lot. But as far as transferosomes are concerned, these modification from lab to industry level is very minimal. Say because the procedure of making transferosomes is very quite simple, and they do not involve any lengthy process as compared to liposomes and all. Further, they also minimizes the use of unacceptable additives. Unacceptable additives means most of the additives or excipients used for NDDS are uh, toxic. They themselves are toxic, or they face drug incompatibility issue. Whereas in case of these excipients, they are readily matching with the body, as well as they are compatible with the drug. Another formulation is polymeric micelle formulation. Now we all know what are micelles. Micelles are a sac or a vesicle formed because of the differences in the polarity. Like suppose when we add soap to water, it forms micelles, and in this micelle, if you add oil, it gets entrapped into the micelles. So we use normally soap for washing the clothes because the oil or the oily stain, lipophilic stain, gets easily taken out, can be taken out by the surfactants. Very similarly, here also these polymeric micelle formulations are very small. The mice polymers they align themselves in this way. Suppose this is a aqueous core or aqueous medium, and in this if you are adding the block copolymers, the copolymers are added. Suppose in water, they if you are adding anyway, they form this kind of structure. They align themselves in this way. The yellow color here indicates the lipophilic structure, and the blue color indicates water, because external environment is water. So like dissolves like, or the two which are attracting towards themselves, they align themselves. So external, suppose the white color area is water, the blue color will attract, or it will align towards the water. Whereas the yellow, if it is not loving the water, they will align themselves and form a separate group. This is called as the lipophilic core. Then if you add drugs, if these drugs are lipophilic, the lipophilic drug core will entrap the lipophilic drug. Now you will notice that these PMs or polymeric micelles, The structure is exactly opposite to that of liposome. In case of liposome, the core was aqueous. Here, the core is lipophilic and the uh, periphery is made up of the hydrophilic material. These are of nano range, so they are mostly called as nanoparticles and have a hydrophobic core. Hydrophobic means lipophilic. And hydrophilic shell architecture, that means the alignment is in this way. This facilitates the loading of hydrophobic drug, lipophilic drug into the core. One more method of using this is suppose for TDDS, like for treatment of cancers or tumors, the hydrophilic chain is substituted, or sorry, it is attached with a targeting molecule. Now this becomes a ligand that identifies this arrowhead, it identifies the tumor receptors, and this green color chain is hydrophilic, water loving, and pink color chain is hydrophobic block. Now what happens is, if you add this kind of substances into water, they self align themselves in this way: the green color facing the water and pink color, so since it is not miscible with water, they align themselves. Now this forms the lipophilic core. If you add the drug, and if the most of the anti-cancer drugs are lipophilic because of high OH present in them. Now these lipophilic drugs, they go and specifically get entrapped into the lipophilic core. That is, here you can see the blue color balls getting entrapped into the central core. Now this forms a cross link. Now this is a transfer section, but if you see the broader view of this PMs, they look in this way, very similar to the coronavirus. The external structure is of ligands and the inner core is made of lipophilic block along with the drug. Another formulation is microemulsion or nanoemulsion. Based upon their size range, they are categorized as micro or nano. Usually these are of O by W type, but also you will find W by O, sometimes O by W by O, or W by O by W. But usually these are of O by W type. Now, how these are prepared is by taking an aqueous phase and a non-polar phase. The non-polar phase usually is an oil which has the lipophilic component dissolved into it. The lipophilic component can be a liquid which is properly miscible with the oil, or a solid, active solid ingredient, even that should be dissolved in a liquid oil. Now these two are mixed with the presence of a surfactant to get either of these emulsions. Like suppose water in oil emulsion, wherein the water is the central part and oil is the peripheral. Whereas in this case, the oil is the central and the water, blue colored water, is the external or a continuous phase. These are extensively applied for veterinary purposes because of their non-toxicity and non-irritant property. The drug is loaded in the lipophilic core. Now here you will notice the structure has been reduced. It is quite similar to liposome, but only a single layer is present for the shell. In case of liposome, there were two layers of phospholipid. That was a bilayer, this is a monolayer. And the central core is a lipophilic in this case, in this picture. These provide an extended release because of uh, direct contact with the tissue. Lipophilic drugs are being used into O by W by O emulsion, or because our WBCs, the neutrophils, they engulf these lipophilic microemulsions, and they take these engulfed particles to the liver or kidney or spleen for degradation. Now, if you want to target your drug towards the liver, this is the best way. That means prepare the lipophilic, microemulsion with the lipophilic drug into it, and then the macrophages will naturally engulf them and carry it towards the liver, kidney, or spleen. So, targeted drug delivery, especially liver cancer or sometimes spleen cancer, can be treated in this way. Some literatures have scientifically proven that pterodon imaginatus is a drug whose anti-inflammatory property has been enhanced when the formulation was prepared into microemulsion. Next formulation is Microsphere. Now, these are usually free-flowing powders, very similar to our normal powders, and they are made up with biodegradable proteins or synthetic polymers as a major excipient. Besides, the drug is dispersed within the polymer, and that means like a chalk and a color. These are spherical in shape, having a size range of around 1 to 300 micrometer. Depending upon them, the size, they are sometimes called as nanosphere, and mostly they are of 200 micrometer, so usually called as microspheres. The way how they deliver the drug are of different through different modes. Like, so suppose this is the red color is the drug and the purple color is the microsphere. In that case, now the if the pH of the site or the target site is increased, in that case, the drug readily gets dissolved into the increased pH because the drug has more affinity at alkaline pH towards alkaline pH. So the drug migrates from the core or from the center of the microsphere diffusing out into the alkaline medium. This is one of the mode. Second mode is that at an increased pH, certain polymers, synthetic polymers, they swell, and swelling of these polymers creates huge gaps amongst themselves or intercellular space. So this swelling facilitates the diffusion or migration of the drug through these gaps. Initially, the gaps were not present, but due to increased pH, the gaps are now created, so the drug is able to pass into the alkaline pH. One more mechanism is by the degradation of the polymer itself. Suppose this is the purple polymer, this slowly degrades in the alkaline pH, and the drug is entrapped at various locations in the polymer. Thereby, as the drug is getting the polymer is getting eroded, simultaneously the drug is also exposed to the alkaline medium. One more mechanism is at a decreased pH. Suppose this is a microsphere at a normal blood pH of 7.4. If the pH is decreased, as is the case in GI or near the tumorous medium or tumor environment, at the tumor or inflammation site, the pH is slightly reduced because of the presence of acids. So there, the entire microsphere breaks up, releasing the drug. So these are the various mechanisms how drug is released into the targeted site. Now, this is how the microsphere appears. Sometimes you can call it as a microsphere because the drug is entrapped into the matrix, or the entire matrix can further be coated with a capsule or can be given a coat or a shell to protect the matrix from getting dissolved or degraded at unwanted site. So now that in that case it becomes a microcapsule. There are several advantages associated with microsphere, like they can be taken orally or can be injected. The release profiles can be controlled depending upon the polymers used. You can um, make a sustained release or a controlled release drug out of it, or formulation out of this. Next, you can deliver the drug at a targeted site by uh, attaching the ligands to the microsphere. Similarly, Zidori oil, which is a natural oil, aromatic oil, along with quercetin, have been formulated into microsphere for their therapeutic effectiveness against inflammation and cancer. Another formulation involves ethosome. Ethosomes are exactly similar to liposomes. The difference is that the liposomes, they have hydrophilic core. That means an aqueous part is present in the core. Here in the core, aqueous portion is there. But as far as ethosome is concerned, the name itself is derived from ethanol. So the central portion usually comprises of ethanol. So now, rest all components are very similar to liposomes. These are also called as liposomes with the core containing ethanol. The vesicles are prepared with phospholipids and with increasing concentration of ethanol. Initially, the ethanol concentration is low, but slowly it is increased so as to form a hydroalcoholic or alcoholic core. Why ethanol is added is because this ethanol facilitates the permeability of the ethosome through the skin. Suppose this is the skin membrane, stratum corneum. The ethanol, it not only dissolves the lipids present in the stratum corneal cells, but also provides flexibility to the ethosome so that they are able to pass through the narrower gaps. The carriers, that means the ethosomes, they can travel up to the blood circulation for effective delivery of the drug. They are also, since the ethanol is present, ethanol, as we all know, is an amphipolar solvent, so it dissolves not only hydrophilic but lipophilic drugs as well. This enhances the bioavailability of both kind of drugs. Example for this is the formulation of ammonium glycerinate to increase the anti-inflammatory efficacy. Ammonium glycerinate has solubility. It is water soluble salt, but um, at the inflammatory side, the polarity is altogether different. So as to penetrate these ammonium glycerinate molecules, ethosomes are formed. Ethosomes, as you can see here, can be formulated for various different purposes, like to deliver hormones. Ethosomes can be formulated to deliver hormones, to deliver macromolecules like proteins, hormones. Cosmetics can be formulated out of it. Then topical drug delivery for DNA in case of skin cancers and all. Then antimicrobial components, which are very heavy macromolecules, and even pilosebaceous targeting. That means towards the sebaceous membrane or the stratum corneal layer. So these are the various modes how the ethosomes can be used. There are various types of ethosomes. Like suppose these are the classical ethosomes, wherein you can find the black colored drug getting entrapped into the core as well as into the shell or the bilipid layer. One of the other mode is, or the type is, by making a binary ethosome, wherein along with the drug, there are presence of other molecules which enhances the solubility or the release profile. Now these red colored dot, they indicate the another alcohol. So this black color is not a drug, it is an ethanol. Here, black color is ethanol and red color is another type of alcohol, like so suppose isopropyl alcohol or propylene glycol, like that. One more way is formulation of transethosome, wherein there are presence of certain surfactants into this lipid bilayer. Now this is the combination of transferosomes and ethosomes. So these are usually employed for better skin permeation. Now the oils here are volatile oil, herbal volatile oils that facilitates the skin permeation. Now we will talk about nanoparticles. These are very famous because of their extensive application not only in pharmacy or medicine but in various other physics or chemistry domains. These are the property of material. It drastically changes when its shape is, or sorry, size is changed. That means if the color, then absorptivity and chemical reaction, these are the properties that changes suddenly when the size approaches near nanoscale. Usually the size of nanoparticle is from 1 to 1000 nanometer, but mostly you will find around 100 to 150 nanometer. So these are the nanoparticles of 100 to 150 nanometer which have wide applications. They have unexpected optical properties. Like for example, if you consider gold nanoparticles, they appear deep red to black in color. Usually the gold should be golden in color, but this is at a macro scale. If you reduce the size of gold, it changes to deep red or black. The unexpected properties, that is this physical property, is because of its surface area. This surface area is the major component that dominates and increases the bulk of the material. If you consider just 1 kg of particles, any particle, let it be iron particle, 1 kg of iron particle, and the particle size is of around, so suppose 1 mm cube. 1 mm cube particle, if it is of 1 kg, and if you compare the same of 1 nanometer cube particle which is of 1 milligram, 1 milligram of 1 nanometer cube particle, these two will have approximately same surface area. Now this is the magic of nanoparticles. Nanoparticles of yellow gold or gray silicon are red in color. Gold nanoparticles usually melt at a lower temperature around, say, suppose 300 degree. But the entire gold slab, if you consider, it melts around 1000, melts to around 1000 degrees Celsius. So this is the change in the physical property. Again, because of the surface area. Even they absorb the solar radiation at much higher rate compared to the thin gold sheets or films. So even nanoparticles can have a wide application in solar panel designing as well as absorptivity is concerned. We'll just have a look at the suspension of nanoparticle. Suppose this is a suspension of nanoparticle. Just have a look at, these are the gold nanoparticles, but at different size ranges they emit different radiations. That means they give different color. If white light is impinged upon it, they give out different shades of color at different nanoparticles. And further, nanoparticles also facilitate formation of suspensions. The suspensions can be formed, and this is because of the interaction of these nanoparticles with the surface of the solvent. Therefore, the nanoparticles will remain suspended in the solvent, and if as compared to their higher macromolecules, they either will sink or float in the liquid. But once you convert it into nanoparticle, they remain entrapped within the solvent, leading to formation of a suspension. There are certain advantages to nanoparticles, like they have a higher stability, increased shelf life, and bioavailability is increased because they're able to penetrate through all the barriers, skin barriers, because of their increased absorption rate. Further, since more amount of drug is can be loaded, the dose reduces drastically. They are suitable for both hydrophilic as well as lipophilic drugs. Besides their advantages, they do have certain drawbacks, like due to their high surface area and energy, they tend to aggregate in biological system. That means they agglomerate to form a larger particle. Now, once they form a larger particle, all the nanoparticle advantages or the properties are diminished. They have high immunogenicity. That means the biological system identifies them as antigen to certain extent to some of the nanoparticles. Further, preparation of nanoparticle is extremely tedious process, and it involves more amount of money or expensive procedure. It is also a lengthier processor, and most of the time this is not reproducible. So these are the benefits as well as drawbacks of nanoparticles. One more drawback is that chance of poor targeting. That means you cannot attach directly ligand, so that target drug delivery is most of the time failed when it is delivered when the drug is delivered through nanoparticles. So these are just the general advantages and drawbacks. It is not necessary that all the nanoparticles have same advantages and same drawbacks. No. So generally, these are the advantages and drawbacks.